for digital system.
Yep, I believe
this is an application of synchronous type of sequential circuit. So Dr. Arosha will discuss about kinds of registers, type of shift registers like operations, synchronous counters, and also synchronous and asynchronous counters, especially when we already have a lab in meeting 6, especially in the sequential ones. Yeah, Dr. Arosha will furtherly explains this about the sequentials and every like possible what is the difference between asynchronous and synchronous, like counters, application of the registers, yeah, and some design in the counters. Please, I think it's okay. Please.
Yep. Is everybody around? Can we start?
Yeah, we can.
All right. So then I'm going to share the screen. Yes. Okay. Hope everybody can see. Is that the case?
I still haven't seen. Yes. Okay.
Now it's okay?
Okay.
Right. Can you see or not?
I can see.
All right. Let me go for the presentation mode. All right. Hopefully, everybody understood a little bit of sequential circuits and in terms of synchronous and asynchronous. So today we are going to discuss about we can call as applications really we usually use for digital system design. So then two important applications you can see is registers, and the other one is counters. So then registers automatically implies actually temporary storage of values. So that's considered as registers. But then shifting bit by bit along the bit sequence actually matters for most of the applications. So in the last lecture also, I was telling you that whenever you press a key on the keyboard of your computer system, so then you know that ASCII code is transmitted, and usually it is transmitted in serial form. For example, like capital A, like probably, I can't remember the exact value, but 20H or 21H. So then in hexadecimal, that is transmitted bit by bit. So 21H in hexadecimal, you know how to represent that. So then shift register is one of the important aspects of really in the computer system, particularly when it comes to keyboard. So then serially it is transmitted and serially entered into the register and then converted, transformed into parallel, so that really 8-bit is formed. So this is very, very important. So then at the same time, really counters are important. The counters means in this case is timing. So then sometime we need really some delay to present really in order to provide other circuits to bring really bits and pieces so that the output generated is on time, rather than really making different outputs at different intervals. So then that's clearly important in terms of applications of registers and counters when it comes to digital system design. So then we try to understand, particularly for starting from registers and then go into counters. So then first we will look at it, what are the operations? As I told you just before, serial to parallel, for example, T entered. So then type of shift registers, particularly as I told you, that really data really as input comes and then produces outputs differently depending on the type of shift register. At the same time, you can have really bidirectional shift registers, one way to move from left to right, the other way right to left, or rotation, most probably. So then at the same time, we can use really shift register for counters. And then we will see some different applications. And then we will go through counters, asynchronous, synchronous, and up-down synchronous counters. So then up-down means counting is increased, and then down counter means counting is decreased. 0 to 9, 9, 8, 7, 6 means it is decreasing, then down counter. So then shift register, so of course, now you are very familiar with, of course, storing binary information in a cell. I believe that really by now you are aware. So then the idea behind really the register, as I told you, is a temporary storage device. So each cell you can construct, for example, using a D-type flip-flop. So then automatically implies one of these block means, one of these bit means really a one bit of D-type flip-flop. For example, of course, you can use JK flip-flop as well. So then like this, for example, in this case, we have 4 bits. So then here also 4 bits. So then what is the meaning of really shift registers? Or how to shift, for example, if you have 1 here, how to move this one into the next cell, subsequent cell, and so forth to produce an output. So then that's more or less what we call as shifting. So then there are different ways of shifting data stored in each of these cell, or in D-type flip-flop, as I told you, is a memory element. So then we can really shift. So then you can see that in this case, for when it comes to first one, you can see data in. Oh, what is the mean? Data in means data comes into really to these boxes, means really D-type flip-flops. Serial in. Why? Because data is received by these D-type flip-flops 1 bit at a time. 1 bit at a time. 1 bit at a time. And then based on the arrow indicated here, so the first bit received here and shift to the right, row 1, shift right. So assuming that the first bit received is 1, then move to the second D-type flip-flop, and then second bit received by the first one is 0. So then 0, 1, and then 1 shifted really to the right, and then 0 shifted really to the second one, and then the next one assuming 1. So then 1 will be the first one. So that really is shift right. Shift right. So then the same way really then you will see that really serial out. 1 bit at a time, really. First bit entered, first data entered, 1 will be released from the data out. So in this case, you can imagine that really. So you know very well that about really computer systems, when it comes to 8-bit data, means really whole 8-bit transmit through 8 cables. 8 cables. Now, in this case, what we have is just 1 cable. 1 cable. That is why it's called as really serial in. Only 1 bit can be transmitted all the time because it is serially transmitted. Very important. Very important. So
Sir,
then,
I think the screen that you share is different from.
Is that so?
Yeah,
Oh,
in my screen, you have still in the not presentation mode but editing mode.
not in the presentation mode.
No, no, no. Still,
Oh.
the screen that I have is still shift registers and counters only.
I will put resume share and then pause. Okay, pause. Good. And then let's see really. Let me see. Sorry about it.
Oh, that's okay.
Let me see here. Let me see this one. Probably it works. Now?
In my share screen is still in the
Is that so?
in the first page, still in the first page.
This is first page means this one?
Yeah, the shift registers and counters only.
But then not moving?
Not moving at all.
Oh. What is the problem then?
Sir, maybe you can try to share all the entire screen of yours. That can make your share screen is like everything you showed to us.
Let me stop share first and then see. Yeah. Okay. So what did you say, Rudy?
Now the shared screen, the one that you shared is only at the beginning of the slides only, not in the when you are explaining. It's already in slide 4, if I'm not mistaken, right?
Yes.
Shift registers.
That's
Yes,
right.
but the screen that I have is still in the first slide.
My computer might be slow.
No, that's okay.
Let's see.
Sorry, sir. I think the screen sharing option is not correct. The first.
Nah,
Yes.
this one, yeah, this is
Now this is visible.
now this is visible. This is the presentation mode.
That's right. Now this is the first slide. Am I correct?
Yes.
And then now let me see. No, just I didn't move it yet. Now?
Yeah, yes. It's okay. It's
okay. Now third.
Yes.
Then fourth.
Yes.
So then letters appear.
Yes.
Moving. Okay, moving letters appear, no? Correct?
Yeah.
All right. So then if nobody has seen really this one, then I will explain again. So then, yes, we are going to look at it, all these registers and as well as counters in shortened form, if I tell you. So then, yes, I was talking about really the binary information stored. So then you know by now that really D-type flip-flops we can use to store data up to certain time. So then that's why it's called as really a D-type flip-flop from one side. On the other side is a data in is always is data out when it comes to D-type flip-flop. You would have learned, and of course we can use JK flip-flop as well. So in this case, you can see that we have 4 boxes. 4 boxes implies 4 bits. 4 bits means we should have 4 D-type flip-flops. So then you can see that when it comes to D-type flip-flop, or each box here, or each D-type flip-flop can store only 1 bit at a time, 1 bit at a time, 1 bit at a time. So you can see here we have an arrow called data in. The idea is that these boxes are connected through just single cable, one cable. One cable means that really data transmission is 1 bit at a time. But you know that like 8-bit computers, we have data bus of 8 bits. So then all 8 bits transmit together in parallel. But that is why we call this transmission as serial. Serial in, data in serially, 1 bit at a time. That is called serial in. So then the idea behind shift register in this case, shifting the bit to the right as it receives. As it receives means as the data type flip-flop receive. So the first bit, let's assume that 1, and 1 will be stored here in the first D-type flip-flop, also called the first box. And then if we use shift right, so then as indicators indicated in the arrow, it will move to second box. So second flip-flop. And then if at all the second bit coming in through the cable is 0, it will be stored in first box, and in second box is 1. And then if we really gain shift to right, the second one and the first one will move to really this. So forth, really that's really 1 bit at a time, shift to right, and the same way through the output cable you get really the same sequence. So this is called shift right, and very important, serial in, serial out, 1 bit at a time. So then of course, the contrary, of course, I'm not going to explain all things like this. In this case, arrow indicates data in from this side. So then serially they shifted to the left, and then data out will be also through 1 cable. So 1 bit at a time. But then this one, yes, little different. You can see that. So data here, really, you can see all data entered to the boxes at a glance, simultaneously. 4 bits will be really added to the boxes simultaneously, but the data out, you can see what we have is a single cable, again transmitted 1 bit at a time. Let's assume what we have really 1 0 1 1. So then entered correctly 1 0 1 1 here, but only thing is that really data out will be really 1 bit at a time. So then only 1 bit at a time. So because we have a single cable, these are really 4 cables are connected together, and then data in simultaneous. So likewise, of course, we can have really the contrary one, the opposite one. Data comes in serially, and then the output will be parallel. Yeah, at the beginning, I was telling you a simple example, like keyboard entered, ASCII code really goes from the keyboard to the register, which is inside the computer system in serial form, and then will produce 8-bit, so that 8 bits will be put or will be really transmitted using data bus of 8-bit. Oh, that is really example, classic example for data in and data out. Keyboard transmits always 1 bit at a time, even though hexadecimal value of capital A, ASCII code, for example, 21H. So it is transmitted from the keyboard to the computer system serially, but then computer wants really the complete ASCII codes of capital A, not that really kind of 1 bit at a time, and then to process what is the letter pressed by you using the keyboard. So then at the same time, of course, you can have data in and data out parallel. So the idea, what is the idea behind that? Okay, we have to store data comes in D-type flip-flop before being forwarded into the next level or next execution. So then that is the whole purpose of it, data in, data out. And then, sorry, I didn't really press serial in, parallel out. This one is parallel in, parallel out. And then this is rotation. You can see rotate right. So what is going to happen that it is looks like shift right in this case, rotate right, but only thing is that last bit will not go out of the box, rather it comes back really to the first box, so that really it is on rotation. So the rotation right, and then this one is rotation left. So then there are many applications when it comes to all this. Actually, if you look at really that ALU, arithmetic logic units, there are many different operations you can see that really carried out this kind of shifting. So utilized some time really for ALU operations as well. Okay. So then serial in, serial out registers, as I explained to you, it's just a short while ago, each box in this slide, each box implies a D-type flip-flop. Why? Because D-type flip-flop can store only one bit at a time. So then actually here's you can see data entered is 1, and at the same time data transmission will occur when, oh, very important, additional element involved in sequential circuits, as you remember very well from previous lectures, is based on the clock. So in this case, you can see that clock is connected to each and every D-type flip-flop. So that really, with one clock pulse, what is going to happen? This one will move to this as input to the second one. So then that's what is going to happen. So then D0 will be really in the output of Q. So that is the main function of any D-type flip-flop as far as you have learned. So then whatever data comes in here will be available in the output through Q0. In Q bar, what you have really is 0. So then that part you know by now, I have presumed. So then likewise, this can be shifted. So shifted. So at each and every clock pulse, one bit is moved. One D-type flip-flop really will be activated and then moved one to the next or subsequent D-type flip-flop. So when receive another clock pulse, then receive, so then send, and another clock pulse, that one will be out of so serial. So then we have 1, 2, 3, 4, 5. Actually, to move this one from here to here. How many clock pulses required? From first clock pulse, move here. Second clock pulse, move here. Third, fourth, and the fifth clock size only what you can get really as the output. So then very important to understand really that, so moving across based on each clock pulse received. But at the same time, the diagram shows only one bit really moving, but not really necessary when it comes to serial data input. So subsequent data will be in the pipeline. It will be the pipeline, and then after one move here, 0 might be here. So then with the moment one move from the second clock cycle, 0 will be moved to the output. So likewise, of course, really you can shift really values, bits really one at a time, and then the output you will get also the same way serially entered data in the output. So then serial data input into serial data output. So this is quite important really when it comes to many applications. Of course, serial data input and serial data output, of course, you would have studied by now. If at all you have not studied, of course, really serial transmission, really we have many examples when it comes to communication links. So then sometime really when it comes to handshaking, and so forth. Of course, if you would have not learned so far, of course, we will see in coming lectures. So in that manner, you can see that we can observe the movement of really the data such a way that really you can see how data is shifting to the right, so that is as highlighted in this case. So then when it comes to initially 0 received from in the first clock pulse, really Q0 you find 0, and in the second clock pulse what happened, that 0 is now in Q1, the second flip-flop, but then the subsequent data received for the first flip-flop is 1. So then likewise, as I explained to you previously, yes, slowly moving bit by bit, depending on the next bit really comes into the, we can call as least significant bit. So F0, Q0. So that really we will be moving forward, shifting really each bit really to the right. So then very important to understand that really, of course, for each clock pulse, so one D-type flip-flop will be moved. So in this case, what is going to happen then? Clock signals is connected to all simultaneously, so that really first clock pulse received, if the data is available in the first flip-flop, so then the data will appear. So then if at all in the fifth clock cycle, this one is here, but then other data will be coming all the way. So then very important to understand how this clock works. Of course, in order to understand, of course, clock means in this case, hopefully you would have already learned before, is really square pulse, series of square pulse. Usually this is generated using one of the important IC called 555. So you can use 555 to generate a series of pulses, series of pulses. So based on the frequency, really you have. So 5 megahertz, 2 megahertz, depending on really the type of frequency you require. Of course, you can generate different type of pulse. So then, as you can see in this figure, clearly you can see clock. Clock means what? Of course, square pulses. Square pulses. So then, actually, we can manage these what normally call as duration, or normally we call as period. Capital T. Capital T can be managed. So then you know that frequency is equal to 1 over T. 1 over T. So if 5 megahertz, so then you can calculate T is equal. So sometime really it is 5 megahertz means really, in nanoseconds you get, am I correct? So then you have to look at it very carefully if I am wrong. So then yes, so microseconds, yes, yeah, microsecond would be the best, I believe. So then you have to really understand perfectly that one without any doubt. So then in that way, this width, you can see that is the period is directly, inversely proportional to frequency. So if frequency is 5 megahertz, so the T will be 1 over 5. You know very well about it. So then this is the capital T. So during this period of the clock, of course, the data input will be moved to the right, depending on really shift register we use. So then in this case, shift to right, if you use, so then you can see in each pulse, so then the duration, so will be really moving really 1 and zeros to. So then after 5 clock pulses, you will get this in. So then moving all the way. So as I explained you, so then in this case, of course, you can see that the Q0 is the last, so that really Q4 in this case really is 1 1 1 0 1 0. So then this is perfectly what you have really in the output as well. So then, but of course, in serial data, just to show only this. So then in the pulse, so you can see that the hold on to Q0 sometime before being changed. That is the key point in this case. So then that's very important. So when it comes to during the clock pulse, how data in Q0, for example, available steadily, so without changing. So then as far as level triggered D-type flip-flop we use, fundamentally we will be having quite smooth right shifting. But of course, really edge triggering is quite really essential to look at it, how the timing can be managed. So in this case, what we have is level triggered. So then one will be maintained until really, of course, really the next clock pulse starts, so that really 0 will be moved. So then that's where really, of course, you can see all the way the movement of the bits will happen towards the end. Of course, you have to look at it this one, you either using oscilloscope or some analyzers available. So you can use those analyzers. So in order to understand this one very clearly, if at all explaining like this, of course, might not be really too accurate. So in that manner, there are many, of course, commercially available ICs you can find or you can buy off the shelf. So then you can utilize for different purposes. So then, for example, one of them is 74HC164A is, of course, using complementary MOS, 8-bit serial in parallel out shift register. So then, of course, voltage and the collector can be really +2 0 to 6.0. So in that way, of course, you can see that really, yes, what we have here is the clock and then the clear. So very important to understand that really these elements, now, for example, in these SR circuits, so whether it is SR or D type doesn't matter. What we know very well that really by default, without doing anything, these circuits might have really values previously stored and available. So therefore, of course, really we use clear signal to clear, and before really start sending really the data appropriate. So then that's clearly important to understand. So clear signals function is to clearing the entire output buffers or Q0, Q1, Q2, Q3. So that really no value, no bit is available in that. So then usually that really has really different state as well. I don't know whether you have learned, but anyway, so then in that way, of course, so then we can see that, of course, in case really we can use so-called you can see the clear signal. It says bar. What is the meaning of bar? Active in low. So clear signal, as far as it is in low, means it is 0 volts. Normally we consider 0 means that really no matter the data you may send through serial inputs, all are clear, all will be clear as far as clear signal is activated. Clear signal, so clear signal should be deactivated if at all we want to really transmit errors. That's very important. So then, as you can see, that as an active low, asynchronous clear. So then in that manner, of course, we can clear the complete all registers in this case are circuits. So then of course data can be entered. So then we can analyze those, of course, using again pulse diagrams, as you have seen. Then the other type of circuit is called as parallel in serial out. Parallel in serial out can be used to convert parallel data to serial form. So then the logic diagram for this type of register is this. So then in this case, what is happening that really we are entering in one first clock pulse received, we enter all data D0, D1, D2, D3 parallel, so that in Q0, Q1, Q2, Q3 you have all the data stored and available. So that really is, we have really, in case 1011 means in D, you will find out that value. So then after the second clock pulse receives, then Q3 will go out, Q2 later on. So then likewise, of course, really. So then in order to construct that type of circuit. Of course, as you can see that you need combinatorial circuits such as, for example, in this case, AND gate. So then we have two AND gates and OR in this case. So that really this output really should go through these to get as D. So then depending on really the shifting occur, and then shifting always occur. You can see that it is connected to this. What is the meaning of that? Of course, therefore we have two important signals. What is that? Shift and load. What is the meaning of load? We want to load the value, as I told you just before, 1 0 1 1. So that means we are loading the value 1 0 1 1 to the D-type flip-flop, and no shifting will occur. How do we guarantee? Oh, this is just, you can see, is a one signal. As far as the signal is in low, we are loading data. We are loading D0, D1, D2. No shifting. Oh, how do you guarantee that? Also, you can see this is connected to the AND, and then this is connected to really, of course, really the load. So then load is 0 means really, of course, through not get, of course, you get really 1. So if both are 1 only, here is 1. So then if D0 is 0, here is 0. So then likewise, of course, really, you can see this cable. This cable is not going through a nut. It comes here down. That means really, as far as this is in 0, this independent of whatever the value here we have, we get 0. So we get 0, independent of the value you have. So then likewise, all are connected, so that really, yes, as far as this signal is in 0, so then no shifting occur. That is the guarantee. That's what is guaranteed. But when the signal goes up, that means really 1, then this has a significance. Where? Of course, wherever you can see the connections. So this connection will be activated, shifting. So if we have here 1 will come, and then 1. So then really, so that shift will occur. So together with the data we have here in Q1, of course, really also this is in 1, and then likewise it will be moved to shift. I hope you understand. So that really, of course, the clock really is synchronous, connected to all D-type flip-flops at a glance simultaneously. So that really, yes. So therefore, of course, you can understand when it comes to parallel in serial out, of course, loading and the value to be loaded into D-type flip-flop will occur whenever the signal is in low, means it is 0 volts. I hope you understand what is the meaning of low. In case really, for example, like this, during this period of time, the loading occurs. So then that's the whole point of really loading. And then when it comes to 1, activated 1, of course it is. So then what is our expectation? Our expectation is we must make sure, if you want to do parallel in serial out, initially this signal should be in 0, because we want to load first the value, then only we want to shift. So parallel in and then serial out. In that manner, of course, we can do. But anyway, this can be done, of course, if you use kind of Karnaugh maps and then state diagrams. You use really, of course, you can obtain these logic gates, of course. But yes, in this case, you can see that we can really prove that how it can be used. So in that manner, of course, really, just this explanation is only 4 bits. But usually what happened that we need usually minimum of 8-bit. So when it comes to really operations, we do digital logic design, always we look at really the data bus. So data buses are all in 8-bit. So then they, I mean, minimum 8 bits, of course, really. So then, yes, manufacturers tend to construct or make really 8-bit paralleling serial out shift registers than really 4-bit. And so not still available, you can really purchase. So there is no. So then in this case, therefore, of course, really we have important really signals here, control signals normally we call. These are control signals. What is the meaning of control signals? Those signals control the movement of data. These signals control the movement of data. So then the first one, just what I explained before, now in the shortened form, shift and load. That's that's what you can find. So then we have an important one. What is that? Clock inhibition. Clock inhibition. So then shift enable, right? So in this case, really, of course, and then clock inhibition. So then clock signal and clock inhibit are connected to common OR gate. So either of these inputs can be used as an active low clock enable with other as clock input. So then data is loaded asynchronously when SHLD is low and move through the register synchronously. That's what I explained just before, but anyway, I will look at it again, how here you can see. So you have to understand the fact that really for the load, actually we have to understand that really loading is not subject to the clock. Very important. That is why it is asynchronous. It's not subject to that clock. Why? Because as far as this load signal is in low, actually data we can enter and then those will be entered. So that is why that is data is loaded asynchronously. But then when load really SH stroke load signal goes high, of course, really, then shifting will start. So that's more or less essential to understand. So then, therefore, of course, really, we have really two important ones, clock and clock inhibit, connected to a common OR gate. So either of these inputs can be used as an active low clock enable with the other clock as the input. So then clock input. So very important to understand that. And then importantly, yes, through when it comes to D-type flip-flop. So then this is, you can see that this is a shift right register, what we have, shift register. So 8-bit, shift register 8-bit. So through Q, what we get is really exactly the data entered through, and through Q bar, still we get the inversion of really the entire data set. And that's also very important to understand when it comes to D-type flip-flops or any type of flip-flop you use. Of course, we have two important outputs, but of course, they are not considered as two different, but the same output, only the inversion. So that's also you have to have in your mind. So then, on the other hand, we can also have bidirectional shift registers. That means really shifting to right and shifting to left. So in that case, we should have we can call a control signal to indicate when to be doing shifting to right and when to be doing shifting to the left. So then, as far as you can see that what we have is digital pulses. So therefore, of course, digital signals, and that makes much easier for us. See, if one signal is in low, sorry, at one instance, really one signal is in low means either it should be left or right. So in this case, for example, it says that left bar means really left will occur, left movement of bit, left shifting of the bits will occur when the particular signal, particular pin is as far as in 0, bits will be shifted to left. As far as this is in 1, bits will be shifted to right. So only thing is that Yes, you have to observe this using, for example, in this case, you can see logic analyzer is used. So then if at all really left signal, left and right, that so-called the pin is in 0, so that means really shifting to left will occur. So then with the timing, you can really observe if you use really, so that I hope that you will do in a practical class. I'm not going to explain because you have to understand here, of course, the concept of left and right, but very important, as far as left is in low, shifting will be to the left, to this side. And then as far as really the signal is really active or in 1, that means the shift right will occur. So that's basically you have to understand. So then that way, of course, we can really do really shifting of really the right and left really can be controlled, as I told you just before, using right left pin, right left pin. And so there's a pin, and then you must make sure that really pulse is entered through that pin, based on really the way you want to shift. And very important, because if you have 8 bits, so you know that really 8 bits really to be really shift to the left. In case you want to get all bits shifted to the left. So that means that really you need how many pulses? How many clock pulses required? 8. If at all you want to shift all 8 bits shifted. If at all you want really all 8 bits to the right shifted, so then you need 8 clock pulses to do the shifting to the right. So then that's very, very important to understand. So without that, of course, really you will not be able to understand the shifting part. So then in this case, what we have Q0, Q1, Q2, 3. So Q0, Q1, Q2. So then later on, of course, we have really others. So then this part is really low, shifting left, and then the other part is really shifting right. So then shifting left and shifting right. So you can observe, of course, if you do really. So then in that manner, of course, you will be able to observe really one time really it is shifted left, in case left is in 0. The other time is the shift in right. So then likewise, of course, really, there are ICs they're available in the market. You can really buy and purchase, and you can use it. So then one of the universal shift register, bidirectional shift register is 74HC194. So then 4-bit bidirectional universal shift register. So as you can see that in this case, so then D0, D1, D2, D3, and Q0, Q1, Q2, Q3. So in this case, what the expectation is, you can see that parallel in and parallel out. So then 4-bit bidirectional. So then yes, we have really quite big number of control signals in this case. So then you can see that's a clear signal as usual. So S0, S1 is we can call as the controlling the complete bit executions, I can call, but not to say that it is just really shifting right and left alone. So then we have really 2 important pins. So shift left and shift right. Shift enable once, that one, depending on really left shift enable, that means we have to shift enable in case of left shift. So in case of right shift, we have to enable. So you cannot enable both simultaneously. That's the key point. You can see that here is R and is L. So very important, you can't do both simultaneously activating. One at a glance, not really both. So then the clock signal. So based on the clock pulses received, only data will be shifted. So then So this universal shift register has both serial and parallel input-output capability. So therefore, of course, really, you can see this shift register we can use really not just really parallel, as you can see on the screen, but at the same time, it can be used for serial. So then this S0, S1, S0, S1 controls that. So these are called, S means select. So select signals, select pins. So selection. So based on, we have two, S0 and S1. That means how many combinations we have. We have 2 pins, means 2 bits. So 4 different combinations. So based upon that, really, the circuit is controlled. Circuit is controlled. Yes, that's very important. So the chip is controlled. So then, yeah. So then in that manner, of course, really, you can do really shifting. So then you can see, as I told you, so usually we call S0, S1 is the mode of operation of the bidirectional shift register. So usually in any IC, you can find these type of signals. In this case, really, what we have really 2 pins only, S0, S1. So then depending on really their values, yes, the operations will be different. So what is the meaning of that? Oh, very important. S0, S1 means is nothing more than what you have internally available, so-called what we can call as, so kind of a circuit you learned really in when, of course, during your combinatorial circuits. So if you remember very well, so we use a decoder. Can you remember? So then decoder, so the 2, and at the output, what you have is 2 to 4. So it means really based on the combination of values of S0, S1, really one of the output of the decoder is only activated. So I hope you remember that. So then similar functionality you find here. But of course, really, we have to be very cautious in this case. So then in that manner, of course, you can find out really when to occur shift right and when to occur shift left and so forth, and then parallel in and parallel out. So then that's what you can see here. So you can see here when the clock signal is in low and then it goes high, if these 2 are in high, no left, no right, only ABCD appears in ABCD. So that means really complete output, really parallel. So then nothing is serial, occurs if at all. Both of them are in high. Both of them are in high. The expectation is that really parallel in, parallel out. Okay. So then likewise, if you look at it, another combination. So then, of course, clear H means in this case really not activated, clear. So then when we have really L, so S1 is L, that means 0, S0 is high. So then what happens really in this case really, of course, right. So then moving into the right. So then likewise, of course, in this case, if at all really left is in H, so then H to L, so then it occurs really. So then, of course, you can see the combinations and you can see how it occurs left to right. So that's what you have to understand quite precisely. So then if it is in LL, no operations there. So you can see no operations at all. So importantly, you have to understand the fact that yes, S0, S1, the one really governs really whether left serial left shift or right shift or parallel or no occurrence at all. So then that's what you can see in this table. And then it so then wherever X means really don't care. So then that one is of course really any input can be, but then no matter whatsoever. Why? Because in this case, why this is XX, no matter the value is, clear signal is activated. So that means really nothing, everything will be low, you can see. So that means really no. So does not depend on anything, does not depend on clock, does not depend on S1 and S0, any value. So then clear has really the upper hand as far as clear is activated, usually activated in low. So then, of course, really no value expected in any of the outputs. So then actually is Q. That is why it's called as low, 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 low. Of course, yes, sometimes this is a little bit a wrong way to say that. But of course, really, for the time being, we can assume like that really is low. Yes. So in that manner, of course, really, you can see that can be activated whether shifting left or right or parallel input to parallel output, depending on combination of values of S0 and S1. So then in that manner, of course, you can do it. So then this entire diagram shows really how it works. So I hope that really you will be able to understand going through one by one. So then of course, whenever clear signal, first we should start really always with the clear signal. Clear signal means that really no matter what is the data are, there will be no operations at all. Then the load will happen. You can see here. So then values will be loaded. So depending on S0 and S1 combination of values, so then different operations will happen. So then as you can see that really after loading what we have really here. So then for example, 1, 1, then what we can expect really all data will be really reflected really in the output. So then later on shift right, because you can see S0 is 1, but S1 is 0. So then that part is shift right. So they just I'm giving you really how this S0 S1 works. So then now S0 goes from 1 to 0, and then S1 goes to high. So then shift left occurs. So then all others will be inhibit. So then nothing will happen. So then that's basically you have to understand in this case. So very important how to manage clear signal, and then how to manage S0 and S1, S0 and S1 in order to do. So accordingly, important signal I haven't explained in the previous slide. It is what really of this. So then shift right enable should be here. As you can see, shift right enable, because during this process, so S0 is 1, S1 is 0. So means shift right occurs. Oh, but very important, shift right enable should happen after S1 goes low, stable, steady. So not that really this shift right should activate somewhere here itself. Oh, there will be a timing really to go really to stabilize really the signal. So some you can see that really we have to really wait at least a half clock pulse to get really stabilized, and then that's how really shift rights will start. Shift right will start. So very important to understand it. Similarly, so as I said, really shift right, so both pins are activated in one. Not that really like what we have seen. Can you remember that really we have seen previously that load and shift. So one pin and then load is bar, and then shift is really in high. So just one pin is used to do that, but here very cautiously we use shift right and shift left using two pins. They activate differently, but both activate whenever it is in one. That is the key point. That's the key point. So here in one, and then shift left all the way 0, that means inhibit, not happening the shift left, and until S0 goes low and then S1 goes high, then after half clock pulse, really we force this pulse goes high. So then only the shift left will occur. So this is very, very important, how to really control that. Yes, clearly important. So very, very important to understand that when it comes to this kind of bidirectional shift registers. So that's where really you should know, yes, control signals, when the control signals are really becoming complex, means more and more control signals are there, control pins are there, you should know how to control those by making external circuit. Very important. You have to make an external circuit, combinatorial circuits together with clock, and sometime probably flip-flops are also required, so that really pulse will be activated on time. On time means depending on the clock. For example, in this case, you can see after this is the first clock pulse, second. So then during the third, only activate really shift right. So very important. And allowing really shifting to the all bits to right, then only you can think of changing S0, S1. You cannot really change S0 and S1 during this period of time at all. Why? Shifting happening. Shifting is what? Shifting the bits happening. In this case, right? Shifting the. So then we have, if we have 8 bits, you have to wait 8 clock pulses so that all bits are shifted. And then we can force, of course, you can see after this only we really change S0 into 0 and S1 into 1, allowing really shift to left, but not immediately. You can see that. So after some time, getting really so stable, yes, the shift left will be activated, allowing really bits to shift left. So then timing really matters. Timing is controlled by clock. So you know very well, clock, but in this case, pulses. So you must be very well aware about period of the clock. If it is 5 megahertz frequency, T is 1 over F. So, okay. So then based upon that, yes, we have to, so then importantly, despite this is really a kind of IC given, it does not guarantee that really shifting will occur by just putting really data through D0, D1, D2, D3. So importantly, we have to manage the control signals S0, S1, SR, SL, very, very important. That should be managed by us depending on the shifting occurs. So then very important to understand that, of course, otherwise it is going to be. So then, yeah, so then here's what we have really other type of shift shift registers. Just we have looked at really shifting bits, probably parallel to parallel, parallel to serial, serial to parallel, serial, serial, all. But then yes, we can use also these kind of registers really as counters. How to count number of pulses, but not number of pulses. In this, our case is actually, our intention is really to count 1, 2, 3, 4, 5, 6, 7. But in a way, really, of course, really, yes. So then we have really different types of counters, shift register counters. So then one called Johnson counter and the other one is ring counter. So then suppose Johnson counter can make really using series of D type flip-flops. So then the simple difference is you can see that the last one will be connected, but Q bar is connected. So normally we call as a twisting on this one. So then Q bar is connected to the first one, first D type flip-flop. So then if it is 1 here, output, and then here is 0, 0 will be the input to D0. So then that's so-called Johnson counter. So then that's very important. Of course, we can make it also using JK flip-flops. I'm pretty sure you are now mastered about really these type of flip-flops. So then JK flip-flop easily can be converted into D-type flip-flop without any problem. So that part you would have understood, and J and K connected, really that's more than enough, really. So then yes, only thing is that really yes, twist is means really actually the bar is connected to J0 in this case, and then the Q3 is connected to really K0. You know very well that obtaining D-type flip-flop using JK, so you normally put here inverter, so then the same happens here. So this is same function, there is no difference. So then yes, so then in this case we don't have really bar. Definitely you should know Q0 Q bar and Q1 and Q1 bar, Q2 and Q2 bar. So then so this underline, oh I can see, yes, underline. Okay, underline means bar, you should understand. So then Q3 bar. Okay, so then yes, this very important. How can we do the counting? So that's the so then in case if we had all really draw the diagrammically, of course, without looking into the clock pulses, you can see that the last one really is connected to yes, Q3 is connected to J0, and then Q3 bar, sorry, J0. So then yes, to restart counting. So then of course that is the whole expectation of this. So this is so-called twist. So then in that manner, of course, really you can use Johnson counter to work as a counter. So then, but yes, you have to understand the way it counts. Of course, really you can see the peculiar characteristics of really this is you can see that in each combinations only one bit has been changed. That's the key. 0 here, 1, and the rest is 0. So now this 1 0 0 0, and then here is 1, just this one change, and then here this one change, and here this one change. What do you think about the rest? Because now you can see that even you know about the counting, normal counting, you can see that this one is 4, this one is like 6, this one is sorry, this one is what? Yeah, so something like that you can see. So then yeah, all is here. So this one is yes. What are the rest of the combinations? Now all are 1. We have to change 1 bit. So then what we can do? Can someone tell what is the next sequence or sequences even? We have really here, you can see Q0, Q1, Q2, Q3. So this is not completed. You know very well about it. So then, so at any, from one sequence to the other, only 1 bit to be changed. So 1 1 1 can change this one into 0, correct? So then you can see 0 1 1 1 0 0 1 1 and then 0 0 0 1. So those are the sequences, really remaining sequences, as you can see. So then initially cleared 0 0 0, and then how the Johnson counter really counts, of course, based upon what? Of course, from one clock pulse to the other, only 1 bit will be changed, 1 bit at a time, 1 bit only change, not really. So then it is very important to understand. So then that you can see. Yes, we can implement using a ring one. Also, we can really implement using D type, and the idea behind the ring type is, as you can see, that really the last Q3 is connected to feedback. So then feedback, so to the first D type flip-flop. So the idea behind, you can see that in this case, it is not a twist, It is rather Q3 is connected to D0. In case of Johnson, so what has happened actually, Q3 bar was connected. So then, yes, then notice the feedback. So then in that form, of course, you can see that we can do the same thing with the JK flip-flop. In this case, a ring counter. So then ring counter, you can see that it is connected. It is not the twist. Here, there is no twist. In case of Johnson counter is a twist, Q3 bar is connected to G0, but in this case, Q3 is connected to G0 and Q3 bar is connected to K0. So then that is the difference. So then this is a ring counter. So ring counter, basically, as you can see that it is a ring. It is a ring, there is no twist. So then that it must be preloaded with the desired pattern, usually single 0 1, and it has even fewer states than Johnson counter. Of course, if we look at it, states, what we have really understood really previously. So then on the other hand, it has the advantage of being self-decoding with the unique output for each state. So that's basically what you normally understand when it comes to JK or D-type flip-flop. So then you know very well that really, yes, as far as the data comes in here, goes out means really it is kind of a self. There is no need to really control anything in that case, not like in the twisted one. So that's entirely different. So then in that manner, of course, you can analyze this one, taking into consideration the waveforms. So then I hope really you will do this in a practical class so that really you will understand precisely. So then, so that really, yes, you will be able to understand how this ring counter works. So then in this case, the for an 8-bit ring counter with a single 1, so then you can see how it really occurs. So then depending on really as we have found out really, of course, based on really if you look at it really what we did, really what we understood. So then in this case, in one clock pulse, what we change is only 1 bit. So then in that manner, of course, really you can make it really also 8-bit counter as well. So then yeah, yes, the importantly what we know really from shift register, not just shift register, so any type of D-type flip-flop. So what in the end, what we have, of course, when one clock pulse entered through really the clock, the data which was available in A will appear in Q7. That's the, so then what is the meaning of that? To propagate A to Q7, take a delay of 1/40. 1/40. Why? Because after clock pulse, really, after one clock pulse, only value of A will be in Q7. So that's very, very important. In that manner, what you can see that any D-type flip-flop means a delay circuit. You want to delay one clock pulse, you can delay. So by introducing, of course, a D-type flip-flop. So in that manner, so shift registers can be used to delay a digital signal by predetermined amount, depending on really the timing, or you can really construct the shift register really as a delay circuit, which we require. So then, can you remember? If you look at it really this, if you remember very well, so here you can see that. So this SR cannot be activated. Unless otherwise S0 and S1 has proper values. So then this is like kind of a delay. not to really go to 1. So then there should be 0 all the time, and then only 1 will the change to 1. So say 0 is 1 also same. Make sure that all 8 bits will be shift right before being pulled down. So then we have to have these number of clock pulses as a delay. So then we have to introduce that. So then shift register is ideally you can use for such applications. That's what really. So then 40 megahertz clock, what is the total delay through the register? So then, as I told you, capital T means really the what we call as really F is equal 1 over T, frequency is equal to 1 over period. Period means you know very well. So this is the period. So then the delay for each clock cycle is 25 nanoseconds. Imagine if we have 8-bit and the delay is going to be 25 nanoseconds into 8 to 8. So that really, that delay happened to produce the entire output. So then this is very, very important to understand, because data in the input will never appear in the output unless otherwise there will be a clock pulse activated through the clock signal. Clock pulse will be available, clock pulse will be activated. Then only, of course, so then the delay is 25 nanoseconds. So very important. But importantly, we cannot really, there is no guarantee that actually after exactly 25 nanoseconds, the data is ready. That is why there should be some small delay really to be available until it comes into a steady state. The data, very important, because people might be assuming that after 25 nanoseconds, okay, data is available and can be used. Actually, steady state will come after some time. So it takes little while. So then, of course, very important to understand those delays. So then in this case, we have 8 bits. So then 8 into 25 nanoseconds, 200 nanoseconds delay. So then whatever data comes in will be available in the output after 200 nanoseconds. So what is the meaning of that? We have to understand very clearly. This works as a delay circuit. Delay circuit, and that is really valuable when it comes to for many applications, as I explained to you just before as well. Activating S0, S1 together with really shift right and shift left. Yes, we have to introduce some delay. So then, yes, we can introduce actually these kind of registers, yes, as really delay circuits in any applications, and not solely shift register applications. For example, even in case of parallel in and parallel out, also we should expect really that kind of delay. So then that is T is equal to 100 nanoseconds. So then data in during 25 nanoseconds, and the data out will be after 200 nanoseconds. And that's clearly important to understand. Another important applications I mentioned at the right beginning is universal asynchronous receiver transmitter. Universal asynchronous receiver transmitter is all the time data propagates serially, 1 bit at a time. Very important. There is no mechanism. The universal asynchronous receiver transmitter really has kind of 8 bits. So then in that way, of course, really what we have to look at is that as far as our data wants to be processed by a CPU will never have an option to process data without using data bus. No. If at all, even you have an external circuit connected to the CPU, that external circuit also should have a data bus. Data bus. It always accepts in a bus. What is the meaning of bus? Depends on the width of the CPU. If at all CPU is an 8-bit CPU, or then data bus is 8 bits. That is how really we determine really the width of a data processor. So that's, you can see that. But UART, all are in serial, but only thing is that when it goes to processor, CPU, we must make sure data will be available in a bus, depending on the type of CPU. In case of 8-bit processor, so data bus is 8-bit. In case of 16-bit, 16-bit. We have to produce in the end so that really CPU can process data. Very important. So then, in that way, of course, really, the shift register is one of the important application. I mentioned at the right beginning, the classic example is keyboard. You press a key, it generates an ASCII code, but that ASCII code will not transmit to the processor in parallel. It transmits in serial because UART is connected. UART is available. UART always transmit in 1 bit, and then we have to use a shift register inside to serial in, parallel out. Serial in, parallel out. That's what we have seen really previously. Of course, when it comes to UART, it's nicely programmed, you know very well. It's a programmable chip, of course, really depending on really number of bits used to start bit and stop bits, of course, guarantees that really it goes in a packet. So that really nicely organized packet form, you will be aware, you will be seen really that transmission occurs. So in that manner, of course, really what I was referring to when it comes to the first slide. So we can go back and to understand really what kind of yes, what we are looking at, serial in and parallel out. Serial in, parallel out. You can see that serial in, parallel out. Serial in, keyboard transmit 21H, how? 0001 first and then 0010 followed. 21. How do you write in binary? 0001 and then 0010. That is how transmit, shift register. Then we have to have a shift register, get 1 by 1 and produce parallel output to connect to the data bus. Very important. So then that's clearly important. We should know very well about it. And then there are enormous number of applications, but of course here what I refer that. So the way really you can see UART transmit is like this. So then start depending on the start bit, it start transmitting actual data until it finds stop bits. So then stop bit is 1 packet of data transmitted. So that really is. So then in the end, before being transmitted into data bus, there is a buffer. Why we require buffer? Oh, of course, you know very well that CPU is faster than really any of the externally connected circuits. So CPU might have really a frequency is much higher than really any of these circuits. Then what is going to happen that really, yes, CPU constantly looking at whether data is available really in the buffer. So buffer means store data until CPU accepts really data from the buffer. Buffer means that it is a buffer which does not allow transmit immediately after generated the data in the output. So in case of shift register, you know very well that really after 8 clock pulses, all 8-bit data are available because shifting occur from serial to parallel, but buffer blocks it. Buffer stores and not put really buffer means that. Buffer, you know buffer very well. So on a road, buffer means you know very well what is the meaning of that. So then this is a buffer. So then it is specially constructed circuits available in buffers. So then buffer is constructed using 0, 1 is usually be used, but then there is a third state. That means it is completely open. The resist impedance is infinity, so that really until really the current flows through or voltage available, impedance will not go down, so that the buffer is always make sure that no transmission occurs. So then third state buffers usually use. Okay, but of course, in our case, in normal life, the counting is, of course, what we expect really to count usually, 0 to 8, 0 to 7, sorry, in case of 3 bits. But you know very well, in our normal life, even we don't like really 0 to 7. What we like is really 1 to 10. So then that part you know very well. So then, so if at all you want to really count. So then, yes, if we have really only 3 bits, so that the maximum number we can count using 3 bits is, 8. 0 to 1, 1, 1, 1. So 1, 1, 1 means 7. So then only you can really count from 0 to 7. So actually you are counting 8. There you got my point, because it starts from 0. But in the normal life, as I told you, we don't like that. So we like really start from 1. So you have to understand that. So then if you look at it really, how these bits are changing, so you can see that when it comes to least significant bit, LSB, so you can see that every number change. You can see every number change. So 0, 1, 0, 1, it looks like a pulse. It looks like a normal clock. Normal clock, 0, 1, 0, 1, 0. Oh, that's perfect. But what about the next bit? Next bit change, you can see, oh, once so then it remains really in 1, 2 combinations and then change. What about the most significant one? Oh, that changed every 4th. In case of 3 bits counter, this is a 3 bits counter, 3 bits counter. So fantastically, we can really represent using we can call clock without any problem. So then like this, you can see it is a perfect square pulse in this case, 0, 1, the least significant bit. But in this case also perfect square pulse, but only thing is that you can see that the period is double of this. This is the period here, and this is the period double, and then this becomes like, of course, 4 times. So then a more significant bit change really is the least really when it comes to. Then of course we have to make a counter so that really counter counts really in this manner. So then you have to understand the fact that really then we have to look at it how the least significant bit should work. So then, and how yes, but in anyway, so then we have been looking at really just to look at it really the counter, but then yes, all the time what we understood in previous slides, what of course, as you may notice that what we understood really in all previous ones is that clock is really inputted to all circuits simultaneously. So you can see here clock signal is really simultaneous. So then clock signal when appears, it appears for each and every D type. So this is we call synchronous. Clock is used to synchronize the complete circuit, all D type flip-flops. But asynchronous means, oh, clock signals is not really available to activate, in other words, all flip-flops involved. Rather, it gives the clock pulse only the first D-type flip-flop. The other flip-flop will work based on the output produced. Oh, now you know. What is the meaning of that? The data from D0 will appear in Q0 after 1 clock cycle, capital T period, after capital T period will appear, and now these clock signals is not connected simultaneously. Usually Q0 bar to connect to the clock of the subsequent D type, or this D type will activate a pawn reaching the second clock cycle. So then, as you can see, or moreover, of course, it is 0. So then, of course, as you can see that, yes, Q0 bar is initially 0, because if we have already put here 1, so then Q0 bar is 0, so then will become 1, yes, during the second clock pulse, So then in that manner, of course, least significant bit and the most significant bit we can manipulate. So then in that manner, Q0 will be changing really like this, and Q2, say more significant bit, in this case Q1, Q0 and Q1 will be really like this. So that's really because you understood now. So this is activated only after Q0 bar is produced. So therefore 2 clock cycles are required to see Q1. Very important. So then, if at all this clock is not available, nothing will be found in Q1 at all. So then D0 make sure that really is guaranteed. So then in that manner, you can see that only the first D-type flip-flop, the remaining D-type flip-flops will be activated based on the output produced from the D-type flip-flop. Otherwise, you can simply say that clock is generated from the flip-flop and not really from the clock as per se. So then, in this case, you can see this is the clock. So then that clock has no meaning to activate really D1. And that is activated purely based on really producing Q0 bar. So that is the clear difference. So that means really that clock pulse, as you can see, is really double of this clock pulse. Double T is double, 2T. So then, likewise, of course, really, you can see in that manner, of course, really, we can really look at it. The counter, we can really then easily can construct like that, because what we understood here, least significant bit is exactly a clock pulse. So the second bit really, of course, you can see is the generation of ones really depending on the double of the clock pulse, and then the more significant bits is really. So then in that manner, of course, if we connect really Q0 bar as the clock for the second, that means the second bit, and then this one connect to this, that is the most significant bit. So in that manner, of course, really we can construct 3-bit asynchronous binary counter. So then that asynchronous characteristics comes when it comes to these kind of counters. So when we require the counting, bit pattern, you have understood that really least significant one really changes the fastest compared to the most significant bit. Most significant is the lowest. So then it always is like, as you have noticed that really, yes, in case of 3 bits, it's like 4 times less speed compared to the FF0 or D0. So then you can also use, of course, really same way of JK flip-flops. So then there is no significant difference here. So then significant difference might be like just short-circuiting J and K. So that's the whole idea, because whatever data we would like to really obtain in Q0, so then in that manner, of course, we can construct. So then in that form, of course, really same waveform I explained really now, bringing back really here. So then taking into consideration how Q0 bar is activated really to operate the second circuit. So then you can see that initially is Q01, and then means 0 means this is activated, and then likewise, of course, really you can see, I believe you should be able to understand without any doubt. So then in this case, what we understand is that really how the counter started. You can see starting from 0, 0, 0 to 1, 1, 1. So ascending order of counting, we normally call as up counter. Up counter. So then up counter means ascending counter. But then similarly, we need also down counter, descending order, starting from 7 to 0 as well. So then, yes, that's also very important. So then asynchronous counters are sometimes called as ripple counters, because stages do not all change together. So the ripple means that. So then, therefore, of course, really, for certain applications requiring high clock rates, this is a major disadvantage. As you have already noticed, really, when it comes to like 3-bit counters, you would have noticed that, really, yes, the so-called clock rates really is 4 times when it comes to most significant bit. So then that's where really you have to understand that what, of course, propagation delay. So then that's of course, when it comes to Q0, the least significant one, but of course, most probably at the end of each clock pulse available within the capital T period, 25 nanoseconds in case of 40 megahertz of frequency, but Q1 is not that. Of course, really, there are significant delays will be propagated. So the moment it goes really higher and higher bits, 3 bits, of course, you can see the delays. Here's introduced, if you look at it, like 3 times. So 3 times. Delays are really like 3, but then becoming really more grave. So then we can calculate easily, of course, that those delays, taking into consideration, as you can see, is delayed by 1 propagation delay, Q2 by 2 delays, and Q3 by 3 delays. 3 delays. So then such delay will be accumulated. So then propagation delay will really be really higher and higher, if at all you use really higher number of bits. So then really, of course, you should be able to calculate those ones. So then, yes, one of the important exercise here from the textbook is, you can see that it says each T flip-flop is negative edge triggered. Oh, there is a little difference compared to really what we have really understood so far. So level triggered and then edge triggered. So level triggered means really certainly the expectation of the data to be steadily available after some time. That is a level triggered. Level triggered means up to certain time. So we allow the data to be really available. So this is particularly important when it comes to CMOS circuits. CMOS circuits has really that little disadvantage over the TTL circuits, so transistor logic. So then it takes quite a while. So then to establish. So sometime really it looks like, for example, a capacitor. You know very well that capacitor really will be charged, not really immediately, over the period of time. So then same applies here. So, but edge triggered means really actually during the particular edge from 1 to 0, is definitely the Q0 or data will be changed immediately. So that's more or less really the expectation when it comes to edge trigger. So because this exercise is about edge triggered. So edge triggered, you can see edge triggered. Immediately it goes up. But in previous slides, what we learned that we have seen there is a slight delay. So anyway, so then in case really we don't, we omit really, of course, the timing diagram. Of course, what we can see that what we have here, you can see, assuming that they have given really propagation delays not 10 nanoseconds, then we have 4 circuits, then 40 nanoseconds. So if the maximum clock frequency is 25 megahertz, so then so then maximum clock frequency, in this case, we can calculate based on the 1/t, that is so-called the total duration. So in this case, really total duration means a capital T we consider the total. So then 25 megahertz frequency maximum. So then to avoid the propagation delay. So very important. So then you look at it, really the complete delay occurred really when it comes to D3 or 4 different types of flip-flops. So then in this case, 4. So then each delay is 10 nanoseconds. 10 nanoseconds. So then the total duration, total propagation delays, then 4 into 10, 40 nanoseconds, then the clock frequency, maximum clock frequency required, I can say easily, to avoid problems due to the propagation delay, it should be like 25 minutes. So this way really you can think of really using appropriate clock before being really experimental, before being connected D-type flip-flop in those in this manner. So very important to understand that really to find out a maximum frequency, and that is really, really necessary so that the data are properly available in the outputs of each D-type flip-flop or JK flip-flop. So yes, so far, yes, well, you know that really what we have really 0 to 7 is not really the practical, there is no practical application when it comes to human being. Human being, of course, we always expect that really counting is decade count or decimal. So then in that way, of course, really what we know very well that really if we start from 0, it should go up to 9. So that is the usual expectation, as you are aware, because it starts from 0 and 9, and then it goes 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 9. You know very well. So then, yes, what is the occurrence? Of course, its counter should start from 0, but after reaching 1, 0, 0, 1, should be then reset and start back from 0. So then reset means, of course, clear signal. In this case, it's clear signal. So then in that manner, of course, really yes. So then this NAND gate is producing from here and then here, so that really clear will be happen when 1, 0, 0, 1 is there. So then that is the whole purpose of putting this NAND signal. So please analyze. I hope that you will be able to do that. I'm pretty sure. So then, unless otherwise, of course, you might not know really the operation of NAND. The introduction of this NAND is really important. Really, it is just to start back really from 0. So then, in that form, of course, you can see that yes, what we have really reset really during the what we can call as 10th clock cycle. It is really cleared, so that really start back from 0. So then clear line. So clear signal in that way is very, very important. So you can see that in case of really you want to use a kind of a decade counter. Yes. So yeah, I forgot to ask, probably yeah. We have really 4 JK flip-flops. What is the maximum number you can count using 4 flip-flops? Just a question. Can someone answer? I was talking all the time. Excuse me. Nobody talks. Someone is there about.
Excuse me, sir.
Huh?
Come on, students.
Isn't 0 to 15?
Yes, 15, but of course, you are correct, starting from 0 up to 15, because J0, J1, J2, J3, all are in one. All are in one means really 15, correct. Yes, thank you so much for answering the question. Yeah, so then in that manner, of course, it is. So then we can also have synchronous counters. So in that case, what we have really, all counters are active based on the first clock pulse received. But then we have to control the counter, because the question is that really what we need in this case is actually counting one by one. So then it is not like the asynchronous counter. Asynchronous counter, what we have looked at really the pattern of bit changes from one to the other. But in this case, we must make sure that really counter counts properly, means it starts from 0, and then because clock pulse will be getting to all three simultaneously. So then in that case, the main advantage of that is, of course, no propagation delay, because the question is really all counters, all D-type flip-flops or JK flip-flops operate simultaneously. So then common clock pulse, as you can see here, is common clock pulse. So we have 3, we can go up to maximum of 8, 0 to 7. Okay, so then yes, in that form, of course, really you can look at it really, the operation of 4-bit synchronous counters by attaching appropriate logic gates to go by really the sequence of counting. So this can be really, of course, deductible or proof using, of course, Karnaugh map, simplify, and then get really kind of, so this we can do as you would have done previously. So that is perfectly possible. But anyway, knowing that really, of course, the counter should operate taking into consideration subsequent bits. First 000, and the next one is 001. So then in that way, of course, we have to introduce the logic gates here. So then to get really all counters get ready to count really soon. So then so then in that form, of course, we can use really this one, a binary coded decimal synchronous decade counter. Importantly, the idea is, of course, really it goes from 000 to 1001. So then we have looked at that one really previously using asynchronous, but in this case, of course, really you can see we are using so then the logic gates we use in this case, of course, just to reset really or clear and then start back. Yes, we can use that. So then in that form, of course, you might be able to experience this, of course, if you use logic analyzer, or sometime probably even oscilloscope. So then yes, in that form we can you can really look at it, the way it works. Yeah, so yes, then in commercially available ICs for different types of counters. So then one of them is 74LS163 4-bit IC. So then you know very well that 4-bit IC means really we can count up to 15, right? So then, but at the same time, we can also count up and down. So only thing is that in that case, what we use really up signals actually use really in this case to count from 0 to, in this case, 3 JK flip-flops to 7. When this goes down, it goes through this. It goes through this NOT gate, and then using Q0 bar, what we do is starting from 7 in count to 0. So then that's more or less the idea. You know that really initially this is 0, 0, 0. And in that case here, what we have is 1, 1, 1, correct? So then, yes, it starts really from, so then you can really try and then see how it works. I have just indicated how it works a little bit. So you better really go and do at home really and see you understand. So otherwise you may drop me really kind of. So then in that manner, of course, really you can find different types of ICs available in the market, and you can purchase and utilize depending on the necessity. And in that way, of course, you can use for different applications. So in this case, the first one, synchronous up-down decade counter with parallel load capability. So ripple clock input and output when the terminal count is reached. Also very important. So then the max min is really for that. So then likewise, of course, you can design synchronous counters. So using state diagram, I hope really you would have familiarized this one. We would have done really many exercises. So then in that case, if you look at the state table, present state really is 0, 0, 0. So then upon the clock pulse, really we have to count next state. So likewise, of course, we can use JK flip-flop, and then we can simplify using Karnaugh maps. So those things I'm pretty sure is straightforward by now for you. So I think I don't need to explain one by one. But of course, if you need, then you have to question later. So you can drop me a question so that I can answer. So then the idea behind really, of course, constructing so-called Karnaugh maps really to provide necessary combinatorial circuits required for each and every JK, J0, K0. So then in this case, you can see that this is perfectly, we need really 3-bit counter. So then we know very well that we need really 3 JKs. So then J0, J1, J2. So then we K0, K1, K2. We have to obtain using Karnaugh map, and then we have to connect appropriate combinational circuits. For example, J0, K0 in this case is exclusive OR, and J1, K1 just AND gates, and then J2, K2 also just AND. So this you should be able to do it. And then here's just exercise also given for you to do that. But anyway, before ending, I want to ask a simple question. Yes, okay. This is of course really 3-bit counter. Assuming that we want to count only 0 to 5, up to 5, 0, 1, 2, 3, 4. What is going to happen to the rest? So what I mean that 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, and then reset back. How the present state and next state looks like. Can someone tell me? As per truth tables, you know. What is going to happen? The rest, for example, 5, 6, 7. Those are not really required because we want to count only 0 to 4, 5. Can someone tell what is going to happen to the remaining? We have 3 additional states. 3 additional states. What are the others? What we do with the others? Okay, you have to think about it. And very important, hope that you remember very well, don't cast. Okay, so then, yeah, so you have to look at it and then yes. So I would suggest also you try, rather counting from 0 to 5, 0 to 4, can we count 1 to 5? Then what are the don't care states? So you better look at it. You better really analyze those, all of them. So then that matters actually when it comes to this kind of circuit design, when it comes to applications. So then people want to count from 1, not from 0. So what is happening to 0, 0, 0? Yes, please look at it. Those are really the things that you have to question, and then look at it. If you know very well about don't care, how to handle don't care, definitely you will be able to manage it. So hopefully you will try at home, and that's the end of today's class. If you have any, I hope can I still go, or already time?
It's already time, sir.
Already time. Okay. I
It's
took
okay.
the exact timing, so I'm pretty sure. Yeah. So you can do many exercises, like what I said just before. Not only the exercise you have here, and then you think about really counters, how you can design different counters in different manner. Yeah. Okay. Do you have any quick question? Of course, I can answer. Otherwise, you can send me by email.
Anyone wants to question? Okay, if no, one thing that before we end this session, that you can, or you still can use the design of the synchronous counters, either synchronous or asynchronous counter, as a scan engine. One of the application of the counters is a scan engine for in our APGAs, especially in Nexus 7. The design of the synchronous counter, you can use it as a part of the component, a larger component of the synchronous counter, a larger component of the design that you are doing. Yeah, remember that, because in our next lab, especially for LA, LB, and LC, in our next lab, the lesson is about how to implement a scan engine using an FPGAs. For example, that our Nexus FPGAs have a common anode, and all the data is connected into one. That is why at the mid examination, when you put a number, every all of the 7 segment is displaying the same value. Now, by implementing a design in synchronous counter, or a counter, and adding a counter, you can make 8 of that displays 8 different types of numbers. That is what we call a scan engine, but it needs a clock, and it also needs a design in either counter or ring counters. That is what we will do tomorrow. Yeah, please, for any one of you that is listening, this is the design that we will implement. Yeah, so I'm hoping that all of you listens Dr. Arosa's lectures today. Thank you, Dr. Arosa. This is for every explanation. I hope that we will see you next week, yeah. Next week, if I'm not mistaken, yeah, Dr. Arosa. Okay. I will end this meeting. Thank you very much. Thank you for the students. Thank you so much, Dr. Arosha, for your time.
Thank you, Prof.
Thank you, bro.
Thank you, bro.
Thank you, bro.
Okay.
Prof.
Thank you, bro.